All right, hey AP Chemistry. So I'm going to continue with doing problems 8, 9, and 10 from your equilibrium problem set number 3. Um, Number 9 is a continuation of number 8. In order for you to do number 9, you need to have calculated the equilibrium concentration, Kc, in question 8. We got a very small Kc, which is 10 to the minus 14th. So I'm going to write the equation again and put the Kc. The equation we have is 2N2O, doesn't matter that it's a gas, plus O2, gas, in equilibrium with 4NO, gas, and the Kc is 3.71 times 10 to the minus 14th. Now, that's a very, very small Kc. The reaction will not go to completion. It's a very small Kc, which means we mostly have reactants and a little bit of products. So let's apply this to this question. It says, using the Kc that you calculated in question 8, what would the equilibrium concentration of NO be if 1 molar of N2O and 2.75 molar of O2 were introduced into an evacuated flask? For this question, this is a question on calculating equilibrium concentrations given only initial concentrations and the Kc. So for that, we always could use an ice table. So I'll set up a nice little ice table here, and we have our reaction already. So initially, we have 1 molar of N2O and 2.75 molar of O2 and nothing of NO. And then in the change section, now this is where we use the value of x. To figure out how much N2O is going to be used, it's always going to be twice the amount for this reaction. So minus 2x. For O2, it's going to be minus x. For NO, I'm going to get plus 4x. Okay? And then in the end, I'm going to have 1 molar, or 1 minus 2x, 2.75 molar minus x, and then 4x. And just to remind you of the Kc expression, Kc, and I wrote it up here in the previous question, but it wasn't big enough, NO to the 4th all over N2O squared O2. And now all I do is plug these values in to the equilibrium constant. I'm going to plug them with the value of x, okay? And I already have the Kc. It's a very small number. We're going to use that idea that it's a small number over here. So I'm going to write it over here all together. 3.71 times 10 to the minus 14th equals NO is going to be 4x to the 4th all over 1 minus 2x, 2.75 minus x. Okay, and now if I wasn't going to make an assumption here, this would be a cumbersome of a problem. I'd have to get like a quadratic and do some crazy rearrangement, but instead we could do something simpler. Since Kc is very small, very, very small, Kc is a lot less than 1, we could approximate that x is approximately 0. So in this denominator, these minus 2x and minus x is essentially 0. That's because what we're trying to say is that this value of x is so small that I'm subtracting a very small number from 1 that I'll probably get 1 again. It's kind of like in my previous question. My value of x is very small. The value of x is actually 0.0025, that essentially these numbers are about the same as the initial numbers. So that's why I had a question like number 8. What happens when the equilibrium constant is so small? It's essentially subtracting a very small number that they're about the same, like 2.9995 rounds to 3. So same thing down here. This value that I'm subtracting is going to be so small that it's going to basically make 1 almost equal to the original value, right? This 1 minus is going to be about the same as this. So let's use that assumption. I could cross out these minus 2x's because I'm saying that I'm going to subtract a very small number. And then somebody asked in class, why can't I get rid of the x up here? Multiplying by a small number is very different than subtracting a small number. 4 times 0 gives me 0, which we know would not work here. 1 minus 0 would leave me with 1. So now subtracting a very small number is different than multiplying by a small number. Just a note right there. Okay, so now I'm going to rearrange and organize all of this. I have 3.71 times 10 to the minus 14th is still going to be 4x raised to the fourth over, since these minus 2x and minus x are gone, it's going to be 1 times 2.75. So it's just going to be 2.75. Okay, now be careful. This is 4x raised to the fourth. To do 4x raised to the fourth, you got to do 4 raised to the fourth, and then x to the fourth. So 4x raised to the fourth, that whole thing, I raise both numbers to the fourth. So this becomes 3.71 times 10 to the minus 14th equals 256x to the fourth over 2.75. And now rearranging, I take this 275 and multiply it up here. These are some crazy numbers, but it doesn't matter. I'm going to take 2.75 and multiply it times this. Right, I'm going to eventually try and solve for x, so I need to get x by itself. So 2.75 times 3.71 times 10 raised to the minus 14th. And I got 1.02 times 10 to the minus 13th equals 256x to the fourth, right? That's by multiplying this by 275, right? Remember how to do algebra. If this was like 5 equals 256x to the fourth over 10, I'd have to multiply both sides by 10 to get rid of that. And so now I'm left with this, x to the fourth. If I want to try and get x by itself, I divide both sides by 256. So I'm dividing both things by 256. So I'm going to divide this number by 256. And I get another really small number. I get 3.99 times 10 to the minus 16th equals x to the fourth. And now I have to take the fourth root of both sides. You could do the square root twice, or you could just do the fourth root if you know how to do it with your calculator. On your calculator, what you could do is math, and I think with this 5 button, it's like raised to the fourth. So if I go back, all right, I'll do 4 math 5 of the second answer. And there is my value of x. So 4 means fourth root. This x button that I showed you in math means I'm going to take this number, and that's the root that I'm putting. And this makes sense because the fourth root of 16 is like dividing by 4, so it's 4. I get the value of x is very small, 1.41 times 10 to the minus fourth. And this is going to be in molar. If I solve for my value of x, I'm solving for a concentration of x in molar. If I didn't want to write it in scientific notation, my value of x would be 0.123141 molar. And now it says calculate the equilibrium concentrations. All I do is take this value of x and plug it in. So if I want NO, it's going to be 4x, which equals this times 4. So I'm going to multiply this by 4, and I get 0.000565 molar, right? I know it says 5.65 times 10 to the minus fourth, but it's the same thing as saying 0.000565 molar. If I want O2, it's going to be 2.75 minus x, which I'm just going to do the math on the calculator. 2.75 minus 0.000141, and I get 2.7498 molar. And then if I want N2O, I'm going to have 1.0 minus 2x. So I'm going to do 1 minus 2 times 0.000141, and I get 0.999718 molar. Now, I don't care how many significant figures you put in here. I'm just doing whatever I found on my calculator. But these are my final answers. These are my equilibrium concentrations. NO is 0.000565 molar. O2 is 2.7498 molar. N2O is 0.999718 molar. And I did that by first solving for x, which is all this work that I did here. And then I plug that value of x into E in the equilibrium section of my ICE table. And that is how you do something like question 9. On the AP exam, you're going to have to do something like question number 9, where Kc is assumed to be very small. Now, I was being a bit crazy and I made Kc very, very small. And you might get a little bit larger Kc values like 10 to the minus 6 or 5th where you don't get such small numbers. But it's still good practice. This is how you do a nice ICE problem given a very small Kc.